Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Beyond the Goldilocks zone, unraveling the cosmic puzzle of habitability. In the vast tapestry of the cosmos, the notion of a habitable zone emerges as a profound testament to our quest for understanding the conditions that could foster life. At its essence, the habitable zone represents a delicate balance between stellar radiation and planetary conditions, where temperatures permit the existence of liquid water, a key ingredient for life as we understand it. This concept has evolved from early musings about celestial bodies capable of harboring life to a sophisticated framework that integrates stellar physics, planetary science, and climatology. The idea initially took root when astronomers first considered our solar system, positing that there exists a circumstellar region in which planets could maintain water in its liquid state. As theoretical models grew more intricate, scientists recognized that the boundaries of this zone are not fixed but depend on a complex interplay between the star's luminosity, the planet's distance, and its atmospheric composition. In its earliest formulations, the habitable zone was envisioned as a simple annular region around a star, a concept that sparked imaginative debates about the potential for life on neighboring planets. However, as observational techniques improved and the search for exoplanets intensified, it became clear that the definition required refinement. The habitable zone is now understood to be influenced by many factors, including the spectral type of the star, which determines the distribution of radiation across different wavelengths. This radiation impacts a planet's atmosphere in myriad ways, affecting the greenhouse effect, albedo, and the overall energy balance. Thus, what might be a comfortable distance from a star in one system could be either too scorching or too frigid in another, depending on the star's properties and the planetary environment. This realization underscores the intrinsic variability in habitable zones across different stellar systems, inviting us to look beyond our local example and consider the broader cosmic diversity. The evolution of this concept has been intertwined with our growing understanding of planetary atmospheres and climate dynamics. In earlier models, the focus was primarily on the incident stellar flux, but as research delved deeper into atmospheric physics, scientists began to account for the role of greenhouse gases and planetary feedback mechanisms. These factors can extend the outer edge of the habitable zone by trapping heat or shift the inner boundary inward by causing runaway greenhouse effects. Such complexities highlight the dynamic nature of planetary climates and the importance of understanding both the external and internal processes that govern them. The habitable zone is thus not merely a static shell around a star but a region that is sensitive to a planet's geological and atmospheric evolution over time. It is a reminder that habitability is a transient state, one that may evolve as a planet undergoes changes in volcanic activity, tectonic movement, or atmospheric loss. Scientific discourse has further enriched this field by exploring the role of planetary rotation, axial tilt, and orbital eccentricity, all of which can influence seasonal variations and climate stability. The realization that a planet's ability to support liquid water might depend as much on its internal dynamics as on its distance from the host star has led to a more nuanced picture of what it means to be habitable. Researchers now consider scenarios in which tidal locking, a state where one side of a planet perpetually faces its star, might create extreme contrasts between a scorching day side and a frozen night side, yet still allow for habitable conditions in the twilight zone between extremes. These insights have spurred the development of sophisticated climate models that attempt to simulate the intricate dance between stellar energy and planetary responses, providing a window into the potential habitability of worlds far beyond our own solar system. The discourse surrounding habitable zones is not merely academic, it has practical implications for the ongoing search for extraterrestrial life. When astronomers scan the skies for promising exoplanets, they often begin by identifying those that reside within their star's habitable zone. This initial filter, while simple in concept, serves as a gateway to more detailed investigations involving spectroscopic analysis and atmospheric characterization. The interplay between observational data and theoretical predictions has fueled a dynamic research landscape, where new discoveries continually refine our understanding of what it means for a planet to be habitable. Each new exoplanet discovery, whether it orbits a bright, stable star or a volatile red dwarf, contributes to a growing body of evidence that challenges and enriches our conceptual models. In this way, the habitable zone functions both as a guiding principle and as a flexible framework that adapts to new scientific insights. Throughout the history of astronomical research, the exploration of habitable zones has inspired debates about the prevalence of life in the universe. The idea that the cosmos could be teeming with planets where conditions might support life has profound philosophical and scientific implications. It compels us to reconsider our place in the universe and to ponder the myriad ways in which life might emerge and thrive under conditions that are both familiar and alien. The very concept of the habitable zone bridges the gap between observational astronomy and the deeper questions of existence, offering a tangible metric by which we assess the potential for life on distant worlds. It invites us to imagine environments where biology could take root in forms both similar to and radically different from those found on Earth. The journey to define and understand habitable zones is ongoing, marked by a continuous interplay between theoretical predictions and empirical discoveries. As new instruments and telescopes come online, capable of detecting subtle signatures in planetary atmospheres, our criteria for habitability are likely to be refined further. Future research will undoubtedly explore how factors such as magnetic fields, planetary mass, and stellar activity contribute to the delicate equilibrium that sustains life-supporting environments. Even as we acknowledge the limitations of our current models, the pursuit of knowledge in this field remains a testament to human curiosity and ingenuity. It is a field where every new piece of data holds the promise of reshaping our understanding of the universe and our place within it, offering glimpses into the profound complexity and beauty of the cosmos. The journey of a star from its nascent stage to its eventual decline plays a critical role in defining not only a static region around it but also a corridor of time during which a planet may remain conducive to life. This dynamic perspective shifts the focus from a mere snapshot of conditions to an ongoing interplay between a star's life cycle and the evolving nature of its planetary companions. As a star ages, its output of energy changes, and this gradual shift can either extend or curtail the period during which surrounding worlds might enjoy stable, life-friendly conditions. The concept of a continuously habitable zone emerges from this understanding, emphasizing the significance of longevity and temporal stability over transient episodes of favorability. Within this broader framework, the delicate balance between stellar variability and planetary resilience is further illuminated by the complex interactions that occur on cosmic scales. The nuances of stellar activity, such as flares and coronal mass ejections, introduce episodic bursts of high-energy radiation that can dramatically alter the surface conditions of a nearby world. These sporadic events, while potentially destructive, also drive a dynamic environment in which atmospheric chemistry might evolve in unexpected ways. It is within these intricate patterns of disturbance and recovery that the potential for biological processes finds fertile ground, offering a canvas where resilience and adaptation might take root. The investigation into these transient yet powerful phenomena reveals a tapestry of risk and reward, where the survival of any nascent biosphere is intimately tied to its ability to weather the stellar tempest. The narrative continues as one considers the role of planetary formation and orbital migration in sculpting the ultimate destiny of a world. The early epochs of planetary system development are fraught with chaotic interactions and shifts that can alter a planet's course significantly. As young planets jostle for position amid swirling disks of gas and dust, their trajectories are often reshaped by gravitational encounters and collisions. These formative episodes, far removed from the calm of a mature system, set the stage for later conditions that determine whether a planet will settle into a path that allows it to experience a stable influx of energy. The aftermath of these tumultuous beginnings leaves behind a legacy written in the orbits of planets, where even subtle differences in distance or eccentricity may dictate the long-term viability of life. Delving further into the subtle interplay of forces, one must consider the impact of a star's metallicity and its implications for planetary chemistry. A star enriched with heavier elements contributes to a circumstellar environment where the building blocks of rocky worlds and complex molecules are more abundant. This chemical bounty not only favors the formation of terrestrial planets but also imbues them with the potential to support diverse chemical reactions fundamental to life. In such systems, the interplay between a star's elemental makeup and the subsequent evolution of its planets becomes a critical factor, hinting at the possibility that the seeds of life are sown long before a planet even enters the traditional confines of habitability. The investigation of these chemical signatures in distant systems offers a glimpse into a universe where the prospects for life are intricately tied to the elemental history of stars themselves. The cosmic stage is further complicated by the presence of multiple star systems, where gravitational interactions create environments that defy simple categorization. In binary or even trinary systems, the gravitational tug-of-war between stars can produce regions where the criteria for habitability are continuously redefined. The intricate dance of light and gravity in these systems gives rise to habitable zones that may be transient or highly variable, challenging our conventional definitions and inviting novel interpretations of what it means to be life-supporting. The study of these systems expands the dialogue beyond solitary stars, encouraging a broader exploration of how multiple luminous bodies might conspire to create pockets of stability amid an otherwise turbulent cosmic milieu. As the exploration deepens, the role of magnetic fields and high-energy radiation emerges as a critical factor in shaping planetary environments. The magnetic shield of a planet, if sufficiently robust, can deflect harmful particles and preserve its atmosphere against the erosive forces of stellar winds. This protective mechanism is not static but evolves in tandem with both the planet and its parent star, adding another dimension to the calculus of habitability. The interplay between magnetic dynamics and radiation exposure highlights the importance of understanding a planet's internal structure and its capacity to generate a sustaining magnetic field. In this light, the study of habitability transcends the simple metrics of distance and temperature, venturing into realms where the internal vigor of a planet is as decisive as its position in the cosmic arena. In the ever-expanding quest to understand the cosmic potential for life, a fresh perspective arises when one turns attention to the broader galactic canvas, where the concept of habitability transcends individual stellar systems and reaches into the structure and history of entire galaxies. At this scale, the distribution of stars, the density of interstellar material, and the frequency of cataclysmic events such as supernovae converge to define what some researchers call the galactic habitable zone, a region within a galaxy that offers a favorable balance of elements and relatively low hazards over cosmic timescales. This notion challenges the traditional focus on a star's immediate surroundings, urging us to consider how a galaxy's chemical evolution, star formation history, and even its spiral architecture might shape the prospects for life. In this context, the interplay of cosmic radiation, gravitational interactions, and the steady replenishment of essential heavy elements creates a complex and evolving backdrop against which life may emerge and persist, an environment that is as much a product of its large-scale structure as it is of localized planetary conditions. Beyond the conventional bounds of habitable zones around stars and within galaxies, the exploration of alternative niches for life has opened new frontiers in our understanding of potential biospheres. Here, attention shifts to worlds that may not neatly fit the classical criteria yet offer conditions that could nurture life in unconventional ways. The search for biosignatures in these realms involves probing the atmospheres of distant planets for chemical imbalances, analyzing the subtle interactions of light with molecular compounds, and considering scenarios where life might thrive beneath icy crusts or in deep, subsurface oceans. These environments, while initially seeming inhospitable, prompt a redefinition of habitability that embraces the possibility of life flourishing in the dark, insulated recesses of a planet or moon. Such considerations push the boundaries of our understanding, suggesting that the capacity for life might be more widespread than once imagined, and that the ingredients for biological complexity may assemble under conditions that defy our Earth-centric expectations. In tandem with these theoretical explorations, technological advances have transformed our ability to study these distant worlds, enabling a level of precision that was once the domain of speculation. Sophisticated space telescopes and ground-based observatories now work in concert to gather data that can reveal the faint signatures of chemical processes occurring on far-flung planets, while computer simulations employing cutting-edge algorithms refine our models of how life-supporting conditions might evolve over time. These technological strides have not only enriched our understanding of potential biospheres but have also sparked a profound dialogue between the disciplines of astronomy, geology, and biology, each contributing insights that converge on the timeless question of whether we are alone in the universe. The collaborative nature of this endeavor underscores the importance of interdisciplinary research, where the synthesis of diverse scientific approaches can yield a more nuanced picture of habitability, one that is informed by both the grandeur of cosmic evolution and the delicate intricacies of chemical and biological processes. This expansive vision of habitability also invites contemplation of worlds that might be deemed superhabitable, planets or moons whose conditions, in some respects, exceed those of Earth in their potential to nurture life. Such worlds may benefit from a combination of factors including optimal planetary mass, stable climates maintained over eons, and perhaps even a richer diversity of habitats that encourage evolutionary innovation. Theoretical studies in this arena explore the idea that life might find even more fertile ground on worlds that, while different from our own, offer an environment where the conditions for biological complexity are maximized. This possibility opens a realm of inquiry that is both imaginative and rigorous, as researchers delve into the interplay between planetary formation, geological activity, and the subtle balances that govern climate and chemistry. In contemplating superhabitable worlds, the scientific community is not only broadening the scope of its search for life but is also re-examining the very metrics by which habitability is judged, considering factors that might tip the scales in favor of life under conditions previously unanticipated. In weaving together these threads, from the galactic tapestry to the hidden realms of subsurface oceans and the promise of superhabitable planets, the modern study of habitability in astronomy emerges as a multifaceted narrative that challenges our assumptions and expands our horizons. It is a story of exploration that stretches from the scale of galaxies to the microenvironments where life might secretly endure, a narrative that is as much about our drive to understand the cosmos as it is about redefining the limits of what it means to be habitable. Through this lens, the universe reveals itself not as a collection of isolated, static zones but as a dynamic, interconnected web of possibilities, each strand of which may harbor the seeds of life waiting to be discovered.